Hello everyone that would be watching this. This is Lucas Namanis and I am here to talk to you guys about normal distribution as this is my video project for my stats class. Let's get going. The objective of this PowerPoint slide is to explain normal distribution to a novice while keeping the content relevant to DS 301, which is our stats course. So a definition of normal distribution can be defined as a continuous frequency distribution of infinite range. Continuous basically meaning variable x can take on any value, meaning it's continuous because there are infinite values that x could be. So normal distribution is a descriptive model that describes real-world situations. Many dependent variables are assumed to be normally distributed within the population. Population in statistics meaning total set of observations that can be made. If a variable is normally distributed, we can make inferences about values of that variable. So another term for normal distribution can be called Gaussian distribution. So what are some characteristics of normal distribution? If you were to draw out what a normal distribution would be, it would be a bell-shaped curve. If you can see as the first image on the right, the bell-shaped curve must lie on or above the horizontal axis. The total area under the curve is equal to 1, and the area under the curve over a range of values corresponds to the probability. Any normal random variable can be characterized by its mean, mu, which is that Greek letter, and standard deviation, which is sigma. Second image on the lower right is a histogram, and histograms are used to summarize discrete or continuous data. It is sort of like a bar chart, but there are no spaces in between. For normal distributions, we follow the empirical rule. Empirical rule, or the 68, 95, 99.7 rule, basically just means how far the standard deviation is from the mean. 68 meaning it's one standard deviation away, 95 meaning that's two standard deviations away, and 99.7 meaning there are three standard deviations away from the mean. You can see in the picture on the right over here that this straight line represents the mean, and it shows that 68 is one standard deviation, 95 is two standard deviations, and 99.7 is three standard deviations away. Moving on to standardized scores, or simply z-scores. The standardized score is the distance between the observed value, which is usually given in example problems, and the mean, measured in terms of number of standard deviations. So the formula is the second bullet point. To clean it up, it's also this picture to the right over here, where the z-score equals the observed value, which is usually given, which will be x in this case, minus mu, which is the mean, and divided by sigma, which is the standard deviation. Values above the mean have a positive z-score, while values below the mean have a negative z-score. There will be a z-score chart in the next slide for examples that we'll be doing. When using the formula, the standardized variable will have the distribution of n of coordinate of 0, 1, which the n just means normal distribution, the 0 is the mean, and the 1 is the standard deviation. Basically, it just means that it's standard normal distribution, meaning that there will be a bell curve shape distribution. Z-scores help us calculate the probability of a certain score and can help us compare two scores from different normal distributions. So here's the z-score table. These two charts may look intimidating, but it's really nothing. You know what? Yeah, let's go over some z-scores. So left side represents the negative z-scores. So let's say we were given a negative z-score, or a z-score of negative 2.14. You would scroll down to the left over here to find negative 2.1. Then you'd see where the 0.04 is. It's right here. So then you just connect basically to this value, which equals 0.0162. If you wanted to find the percentage from the decimal, you move the decimal point over 2 times and it would be 1.62%, because all these values from here this way represent percentages. So let's try a positive z-score now. Let's do 1.25. We would go down to 1.2, go to the 0.5, and you would find the number that's in between here, which would be 0.8944. Turning that into a percentage, once again, move the decimal point over 2 times, you'd get 89.4. Sorry, my handwriting is atrocious. All right, example time. Let's see if we learned anything. So, question is asking SAT scores on the math section have a normal distribution with a mean of 515 and the standard deviation of 100. So keep in mind, the mean is 515 and the standard deviation is 100. What is the probability that a randomly selected test taker had a score less than or equal to 600? So 600 is the given value here. So if we remember the formula back from a couple slides, it's the z-score equals x, or 600 minus the mean, mu, over standard deviation, which is sigma. So I did it right here. So I'll just still show you 600 minus 515 over 100 equals, if you put that into the calculator, comes out to be 0.85. So once you get the 0.85, then you go to that z-score table mentioned earlier, last slide, and you would look up 0.85 because you are looking for less than or equal to the z-score. So when you find it on the table, it would be 0.8023, which would make it 80.2% of test takers had a score of less than or equal to 600. Next one. What is the probability that a randomly selected test taker scored higher than 600? So nothing has changed compared to the last one, other than we're looking for people that scored higher than 600. So the calculations here are still the same, except once we get to this part. What's different between these two? You see that this one's less than or equal to, but this question's asking for higher than, so we're looking for the z-score being greater than 0.85. So if we look that up on the table, it's still going to be 0.8023, but since we're looking for higher than 600, we're looking for the other side. We're looking for who scored higher than 600 when the problem before was asking less than or equal to. So you would subtract 1 from the z-score to get 0.1977, which would equal 19.7% of test takers scored higher than a 600. Let's wrap this up real quick. So we're looking for the probability of the z-score being less than negative 1.28. If we look at that on the z-score table, we would come out to be 0.1003, which is closest to B. All right, next one. We're looking for a z-score that's greater than positive 1.28. So that would come out to be 0.8997, which would be closest to D. And the probability that a normal random variable is less than its mean would be 0.5.